planet orbiting a star. And of course, it doesn't stop right away like that. So what you see is, oh, this doesn't want to go, huh? Well, I hope you caught it. No. Okay. So one of the ways that you can find an exoplanet is that it goes in front of the planet, which means a little bit of the star in front of the star. So the starlight is a little bit less, and you can detect that. You can see these periodic dips in a star's brightness, and that's how you can find an exoplanet. The other thing that maybe you saw is that the star wobbles a little bit too. And so we can measure the Doppler velocity of the star itself. And if it has a periodic variation, then we can be pretty sure there is something else orbiting around the star. Just to show you some recent things that we did at Lowell, what you see here are curves in basically in time and in Doppler velocity. And this is a planet where we saw, a star where we saw two planets already, the top two. The bottom two are new. We just discovered those fairly recently. And the way we express this is in velocity, kilometers per second. Actually, if you look carefully, it's in meters per second, right? So a planet down here, that runs at about 1 meter per second. I can probably walk very fast like this, right? So that's about the speed that we can detect remotely. The instrument itself goes down to about 30 centimeters per second. What have we found? Well, every black dot here is an exoplanet that was discovered. And it's shown here at the bottom as distance from the star versus the exoplanet mass. And for comparison, you see the Earth and you see Jupiter. And pretty much everything we have discovered is closer to the star and is more massive than Earth or even Jupiter sometimes. So the reason that we see mostly massive planets close to the star has to do with a bias in our observations. Planets like the Earth are incredibly difficult to find. It takes a year to get one nice wobble in our measurements, and it is a very small signal. The Earth is at about 10 centimeters per second. So that's still basically impossible to find. The few dots you see around the Earth, those are transits, where we see a minute lowering of the brightness of the star. Proxima b was recently discovered. Proxima Centauri is the closest star to us, and the planet was discovered around that. And of course, this is really what we would like to do. We would like to see that planet. We only know its presence there because we have seen a Doppler shift. So to make real progress on finding life on other planets, for example, on exoplanets, we have to take images. We have to see these exoplanets directly. And so here is maybe the most well-known example of exoplanets that were directly imaged. You see 3 on the right. There is a 4th one on the top left. And that's, these are very young, very massive planets. We see them because they're so young that they're still contracting. They're still sending out thermal energy, and that's actually what we see. Nobody has seen anything like the solar system. Not a single exoplanet has been seen in reflected light. Like we see all the planets in our solar system is all reflected sunlight. So how difficult is it to see reflected light? Here's the solar system. If we look at Jupiter, Jupiter is about 1/1000th the brightness of the sun. And the Earth is about 10 times less than that. So this is really tricky, trying to see a little tiny dot that's 1/1000th times fainter than what you see the star at. So even as a scientist, you know, 1 billion, or billion, 10 billions, who cares? It's a lot, right? So how can we imagine this? Well, imagine that the star is Mount Everest. right? Instead of looking at intensity, we're trying to find something that is somewhere on the slopes of this Mount Everest and is a billionth of the height of Mount Everest. Well, an equivalent thing here would be a red blood cell for Jupiter, right? So imagine you have to find a red blood cell on Mount Everest, and all you have is really a device that tells you how much you are above sea level. That's about how difficult it is. And you might think that, well, a star is not really like Mount Everest. I'll show you. Yes, it is, unfortunately. So how can we do this? How can we hope to actually achieve this? The really great thing is that big telescopes are under construction right now. This is the European extremely large telescope, a 39-meter telescope that's under construction in Chile. They're getting there, right? So in about, I don't know, 4 or 5 years or so, we can actually use this to look for exoplanets. So let me show you how this looks like. Here is a, oh no. Microsoft says it has to contact someone. Okay. The first problem we really face is that this is how a star looks like if you look through a telescope. It's not a nice single little dot. Those of you have looked through a telescope, you have probably seen that. Okay, so this movie doesn't work here, unfortunately. But imagine this cloud here just going like crazy. Not staying stationary, wobbling around, changing all the time. And the reason for that is turbulence in the Earth's atmosphere. There are temperature variations in the Earth's atmosphere, which mean that light going through different parts of the atmosphere takes different time to go through. And that creates a huge mess. So what can we do about this? Well, there's a very nice technical solution, and that's called adaptive optics. Adaptive optics allows you to reverse the effect of the atmosphere. You see light coming in from the top, from the telescope. It hits a mirror that we can deform in real time. So a good mirror these days is 4,000 actuators, positions where we can change the shape, and we do this a few thousand times per second. And then you reflect off this. Everything comes in as nice, flat, like in space, what we call a wavefront in optics. It goes to the science instrument, and the residuals also go to what we call a wavefront sensor that measures the difference from a flat wavefront, and it reshapes the deformable mirror to correct again. Now let's hope that this works. Okay, so this is the turbulence here that you see, and now the AO was switched on, and you suddenly see an ice star, and you actually see a companion. That's not an exoplanet next to it. That's just a binary star where you have two stars close together. So, okay, we have adaptive optics. Sounds like, okay, not such big a deal. Well, it is actually still difficult. This is an image from the Hubble Space Telescope. And you can see the stars are not nice dots here. All the thing around it is really light that's coming in here. And what happens is you see this kind of the X shape, and you see this halo around it. That all comes from the optics that are not perfect. It's diffraction. And so even if we would go in space, it is still very challenging. How challenging? Well, this wavefront, we can calculate how, if we want to see Earth, for example, and we want to measure oxygen in the Earth, if we would look from far away, this wavefront, this mirror, has to be adjusted to 1/10 of a nanometer RMS, right? That's about 20% of the spacing between silicon atoms and the processor in your phone. Right? So this is really subatomic optical precision that you need to do that. So this is why it is so difficult. But we're not done yet. The problems just keep coming. So part of this halo that you see here, that has to do with what we call diffraction. It is the effect that we don't have an infinitely large telescope, but you have a finite aperture, 2.4 meters on the Hubble. So if we look at this and say, let's take a telescope. It's optically perfect, but it has a circular aperture of a certain size. Then the star we do a crosscut logarithmic scale. You see it on the right here. It goes down to maybe 10 to the minus 4. But for seeing the Earth or Jupiter, we need 10 to the minus 9, 10 to the minus 10. So even if we had absolutely perfect optics in space, we would still be screwed. So what can we do? We have to get rid of this light around the stars so we can see exoplanets. Well, one of the things I've been working on with my group is that it turns out you can actually, instead of having a perfect telescope, you make it imperfect in a very clever way. So what you see at the bottom left here is the ripples that we introduced on the telescope mirror. It's a very small ripple. It's a few hundreds of nanometers or so, but very controlled. If you now do a cut through the star, what you see here is on the right. So on the right side of the star, you suddenly have a hole there. You got rid of all the diffracted light, and you could reach what we have, what we need to actually see a planet there. So this is the theory, right? You also have to be able to do this in practice. And the whole thing here, we call this a coronagraph. Now, when people mention a coronagraph, they all think it's like the number of corona infections as a function of time. But this is the older version of a coronagraph, where we do something to the telescope to actually get rid of the diffracted starlight. So we can, for example, produce something. On the left, you see a telescope, a fairly reasonable, realistic telescope, how a star would look like. And then on the right side, you see how it should look like when we put one of our coronagraphs in. You see that you still see the central star, but now around it you have a nice dark ring where you see planets. And again, this is theory. Let me show you how it looks in practice here. This is actually on a telescope. And so we see the central star. We see very nice dark ring around it. Of course, it's not perfect. Nothing is perfect in real life, but it works. And you know what? We immediately see that this star was not alone. This little blip there right outside of the star, that's actually real. That's a companion star. How much do you guys know about optics? Is that a lot of interest or more on astronomy? Okay, so you can now do even crazy things. You can now start to tackle another problem. So one of the issues with adaptive optics is you see the light goes into the science instrument, into a camera, but also some of it needs to be reflected into the wavefront sensor so we can do closed loop control. Now, these are two optical paths that are slightly different, which means that any difference between them leads to errors in our image. So we came up with actually new schemes where we use holograms to actually create additional information in the image. So here you see a star, but then around it we make this cloud of points. And this cloud of points tells us, for example, what the error is between these two paths. I don't want to go into the details. On the top is if everything is perfect. On the bottom, you see how it looks like when we have a problem. But one of these dots becomes very sharp and the other dot goes basically away. And that tells us exactly how this wavefront aberration looks like, and we can correct it. These days we do even more crazy things. We can make coronagraphs. We can split the light, look at different things on different sides of the star. We can add patterns outside of the star that all help us to determine what is real and what is not. So based on that and many other developments that we did, we actually got some very nice data. I think this is the one that I'm probably most proud of. This is the first exoplanet here, or let me first explain. Do you guys have a pointer here? Well, I'll try to explain it. So,
and so it's this button right here.
Okay. that one. Yeah. Okay. Sorry, I'm still old-fashioned here. So here is where the star would be. We have done such a fabulous job, you don't see it at all anymore. This is a planet here that was known. This planet here we discovered new. This is the first exoplanet that was found with laser-guided adaptive optics. So we actually sent 4 laser beams into the sky. They reflected at an altitude of about 90 kilometers. We used those as artificial stars to exactly determine what the atmosphere was doing and then corrected it. But on top of that, you know, just taking images of exoplanets is not very interesting, right? You really want to know what they're made out of, how big they are, how hot they are, and so on. And that's what we call characterization. And so in this case, actually, we used an instrument on the 8-meter very large telescope in Chile that was designed to study galaxies. But we decided, let's look at an exoplanet with it. And so with that, we actually could get a spectrum. So every pixel that you see here, we get a complete spectrum, the light, the intensity as a function of wavelength. And so what you see here are different boxes. The yellow ones here, these are like control boxes. We just put them around to see what it is. But then the red here and the purple box here, those are the spectra. And unfortunately, I somehow cut off the wavelength, but this is exactly the wavelength of hydrogen alpha. So you see a huge emission line in hydrogen. What is that? Well, we actually see these planets are still forming. And so they're circling in a cloud here. Other pictures show a nice cloud around here. They still run around in a gas cloud around the star, and they suck up the hydrogen. The hydrogen kind of falls onto the planet, and as it crashes, that shock creates emission in hydrogen alpha line here. So this is not only the first planet here that was discovered with laser-guided star adaptive optics, but these are also the first spectra of exoplanets that are still growing. So there's a ton of good stuff we can do these days. But I wanted to talk about another aspect that we have been working on, and that's polarimetry. Who knows about polarimetry? Polarized sunglasses. It's the crazy aspect of light you never want to think about because it makes everything more complicated. So why is that interesting? Well, when you have a star here and star shines light to our eyes or telescopes, the star is not polarized. There's no preferential orientation. There's no process that makes it polarized. However, when you scatter light off here, then this scattering process polarizes the light. So one of the ways to see things around stars more easily is that you actually look at the polarization. The star should have no polarization. Anything around it that scatters light should have polarization. And so let me go a little bit here. There are different types of polarizations. Light is a wave. Light can wiggle here just vertically or horizontally, but it can also go crazy in a circular corkscrew fashion. And that's what we call circular polarization. And I'll show you interesting things from all of these. So it's because light is a vector wave. It has a preferred orientation in which it oscillates. That is basically the polarization. These are all things I did with my students when I was in the Netherlands. I moved to Flagstaff a little less than 2 years ago. I still have 6 grad students in the Netherlands, so we're still doing quite a bit. This is how we go to a telescope. Normally you sit in a nice chair somewhere warm and have a screen and somebody who helps you, and it's not very old-fashioned anymore, right? You just sit in front of a computer screen. Well, we're a little bit different. We do a lot of experimental things. So we built instruments. We change them every time. It's very people-intensive, but we can do things that nobody else can do. So this is some of my students at the telescope. And then you look at this here. These are 2 stars. You just see them in intensity. And now I can show you how they look in polarization once we measure the polarization of the light. And everything around it lights up. Right? With the polarization, we can see everything that's around the star. And with this trick alone, we get a reduction of the starlight by something like 10,000 to 100,000 times. There's no adaptive optics here. There's no coronagraph here. Right? So using polarization is another way to do things. Just as an example how powerful this is an image here that was taken from the Hubble Space Telescope. It sat there in the archive. You see different features. Not, what is it? What of these things here streaks out here? What is real and what is just diffraction at the Hubble Space Telescope? Well, we can look at it from the ground and measure polarization. And only things that produce polarization is something that circles around the star. And so on the right here, you see our measurements. Here's where the star would be largely unpolarized. But then you see right next to it this big chunk here, big whopping polarization signal. So we actually know that this thing here is real. This is a real cloud. And then we could actually use the Hubble data and figure out what this cloud was made out of, how big the particles were, what they were made out of. We do this, of course, also on the big telescope these days. So this is an example from Sphere on the 8-meter VLT. That's probably our best polarimeter right now. And here is a star, and you can see all these kind of rings around it. That's what you have also seen probably from radio telescopes, where you have these disks around stars, and you have gaps that are probably formed by planets or have something to do with planets. So we can see this by looking at the polarization of light very easily. And the big advantage of looking at polarization, particularly when you look at it as a function of wavelength, is that you can say how big the particles are and what they're made out of. If you only look at the intensity, you cannot distinguish between size and composition. So this allows us to figure out what's going on around planets. So I said in the beginning, the real driver is, are we alone? So how would we find life on exoplanets? Well, we could look for methane, right? Maybe, but methane is very unstable. There's also methane on Mars that's not coming from life. We could try to look for oxygen, right? So there are a few gases that you might look at, but we don't really know all this exoplanet physics well enough to say which gas is now due to life and which one is not. One way to look at life is to look at something that's called homochirality. So you probably know that DNA is twisted all in the same way. If you look at sugar molecules that are made by sugar beets or sugar cane, they're all twisted the same way. Right? You can look at chlorophyll in a plant. It's always twisted the same way around. Actually, for us, it can be very dangerous if we ingest anything that's the wrong way around. Right? So if you go to a pharmaceutical company, they need to have 99.99% or whatever going the right way around. And so this is one of the unique signs of life. So the question is, can we look from afar and actually detect this? And we have worked on this for, I don't know, it's probably 15 years or so that it took us from the initial idea to actually getting things. So we built something we call TreePol. It's the tree polarization measurement device that we have. So you can look at things in the lab. It looks at leaves. It looks at microbes. These days we have a version that flies on balloons and helicopters, and the next version in the lab right now that will be made such that it could fly in space. But of course, as you know, all these things take a lot of time. So here's a lab measurement. It's a tree leaf or some bush or whatever that we put into the machine and just looked at it for a few days. And on the left side here is the fresh leaf here. Down here is the circular polarization signal that reflects. And so when you send light onto that leaf, because the molecules are preferentially twisted in one direction, the light that is reflected will be slightly circularly polarized. And so we can measure this here, circular polarization. You see, it's a very small effect, much less than 1%, but you see a nice peak here, just about where you would expect it from the absorption in these leaves. And then after a week, the leaf was firmly dead. It's all gone. So then we developed an instrument that we could take to at least have it look outside. And that's really where it became interesting. So our student, he looked at the forest and saw a nice signal. And then he looked at the soccer field and he didn't get a signal. And he was like, what's wrong? What's not working? I'm tilting this instrument a little bit and suddenly the signal goes away. So in the end, he decided to go over there, and it turned out it was astroturf. So this was like, he said like, aha, it works, right? You can really detect life remotely. These days we can do things like I could point the instrument at your shirts, and I could tell you whether it's synthetic or it's cotton, not just from the reflection signal. So that's a really interesting thing. So this is how we think maybe we could find life by just looking in an exoplanet. So these days we do things like we fly in hot air balloons to figure out different locations and what signal they have, and then try to figure out what would be the signal of the whole Earth. Probably the most prominent way to do this in the end is if you have some water planet that has all kind of algae on it, that would probably give us a very, very strong signal. So we'll see. I wanted also to take a few minutes to talk about spin-offs, because astronomy is something where you say like, yeah, whatever, okay, it's nice, it's interesting, what is it good for? And I thought I'd just show you a few of the things that I developed with my students that simply came out of what we were doing for astronomy anyway. So I've talked about adaptive optics, making images sharper. We developed, together with Nikon, we developed a microscope that has adaptive optics. And what we're doing is we're looking inside tissue. So we're not looking at the top of tissue, but you go inside tissue. So in this case here, these are breast cancer cells. And when you go through tissue, I mean, just look at your skin, that is not a nice optical thing to look through, but it's a mess, right? And so with adaptive optics, we can basically make it then very sharp inside. And you can easily see how much better. This is the image with the AO off. This is with it turned on, how much better you can do. So if you now go into the literature, there's a ton of people doing this. The other thing has to do with climate science. In the past, or I'll show that at the end, one of the really huge unknowns in climate science is what aerosols do. So very small particles that float in the air. We all have seen forest fires recently. That's aerosol, right? Stuff in the air, very small particles. They're so small they don't come down, they just keep floating in the air. And the last instrument that NASA built was about 1 cubic meter, right? So a few of these chairs here together. We managed to do the same thing, same type of measurement with polarization in a device that is way bigger than life size here. So it's a few by a few by a few inches and about 2 pounds. Right, so we built the prototype, and then since I'm here, I have to show an airplane, right? Otherwise, I would fail the test here. So here is an ER2, and we were actually lucky enough that one of our instruments went into one of these pots here. And NASA actually liked it so much, they used to fly it over California when there were wildfires. And then, of course, you know, people start really getting interested. And Airbus decided to actually build one of these things. And so this is Specs 1, all built on our polarization technology that we developed for astronomy. It has these tiny little telescopes here that look in different directions on the Earth. And this is ready to be launched in, 55 days, I think. So It took about 15 years from us having some ideas on a sheet of paper to actually getting it built and flying in space. The other thing we did was we went the other way around, and we actually built a version of this to put on a cell phone. So this is what we call iSpecs. Used to be attached to an iPhone. I'm sorry, it's pretty old by now. Phones develop so rapidly. But we basically used exactly the same technology to measure polarization very easily. And here is a spectrum. This is a spectrograph here basically. This is a spectrum if there is no polarization. And this is how our specs here works. When you have linear polarization, it introduces a modulation of the intensity. And the depth of the modulation here tells you how strong the linear polarization is. And the location here, so the phase, so to say, that tells you what the orientation of the linear polarization is. So we actually produced about 10,000 of these things. We distributed them. We did measurements in the Netherlands. We had like 3,500 people measuring with their cell phones. They measured the sky, and out of that we could derive what was in the air. And then we wrote the paper, and we actually found a journal that allowed us to have 3,500 co-authors. So that was fun. Maybe another fun thing here is this one. There's an artist in the Netherlands, and he wanted to make a rainbow, a big rainbow on the train station here in Amsterdam. And there have been many artists who tried to make rainbows. And they all think, like, how do you create the rainbow spectrum? You take a prism. Right? And I know one guy, he built a huge prism here in the US. And then he shined light through, and what happens is that red is at the bottom and blue is at the top. You don't get the correct thing, because if you look at actually how a rainbow goes, you get more than one reflection, which kind of flips things around. So with our technology that we developed for coronagraphs, so getting rid of the starlight and making it dark around the star to see exoplanets, we knew how to calculate things and produce it and actually have this huge rainbow here projected. Right? So sometimes it is completely unexpected. You work on seeing exoplanets and suddenly can make beautiful art with it. I think, I can skip this here. This is just where we are. And I'll leave it up here with the Lowell Observatory opening times. I have to say these days, Monday and Tuesday, were closed. I need to update that. Sorry about that. So, thank you for your attention. If there are any questions, either in the room or online, happy to answer those.
Do we have any questions today for Dr. Keller after we say thank you to her? Oh, come on, guys.
Okay, so the first three who ask a question get a free entry to Lowell Observatory.
Oh, okay. Students, come on, you gotta have a question of some sort.
All the cards are right here.
Come on, have you guys gone to Lowell yet? It's so much cool. It's so fun. I'm tempted to ask 3 questions just to take my family.
You didn't read the fine print. Yes.
So this was like a lot of different work. You said it took 15 years to get from that idea on paper to having NASA construct that thing.
Yep.
Is that and then there were some other projects that I don't know that you explicitly said like a time for to get kind of that physical progress from like theory into experimental. Would you say that 15 years is like fast or slow, or how would you say that compares to other developments that you've done? Just because I don't have any experience with kind of that process of going from theory to experimental.
Well, I mean, 15 years is fairly typical. It's 10 to 20 years if you want to do something in space. Now, you have to understand this is really the full-blown thing, right? This is not a CubeSat that may or may not work. This is a thing where it has been tested, forever. There's a whole crew ready to take the data and get the science and the information out of it. So if you want to do something on a CubeSat, of course, you can go much faster, particularly these days when there are so many launch options. Can I have you hand out the cards?
So now that we have James Webb Telescope, is there a way to adapt the telescope to using this polarization technology?
Nope.
No way, huh?
Unfortunately, the 10 to 20 years also tells you that everything on JWST is something like 10 to 20 years old. Right? So it's not particularly well made for looking at exoplanets.
Copy that.
So there are a few things that we can do on it to help, but it's in L2, right? So it is about 1.5 million kilometers away from the Earth, rotates with the Earth around, so that's nice. But you can't really get anything there to fix it or to add. Not like Hubble, where you could send up a shuttle and build in something new.
So is there any plans of sending up some kind of space telescope to use this technology, or?
Yeah, so there is the Roman telescope, which is based on some unknown spy satellite hardware that was laying around somewhere. It's a 2.4 meter telescope that has two aspects. One is for cosmology, make images of galaxies and galaxy clusters, but it also has an experimental exoplanet instrument on it. And there is polarization on it. Okay, I could give you another lecture on where the problem is. It turns out mirrors don't reflect the way that you think mirrors reflect. And that makes polarimetry with that device or that telescope very difficult. It does have a polarimeter built in, paid by the Japanese, but nobody has really figured out yet how to use it. So some of my postdocs put in grants to actually figure it out.
All right. Well, thank you.
AJ.
I'm loud enough. I was going to ask where this research is going in the future. Like, is it just optimization, or is there like further projects that are in mind?
Oh, there's a ton of stuff. Every time you do things by a factor of 10 better, you see something new. And typically it's little effects that you were not aware of. So let me talk about how a mirror reflects. I don't know, does anybody know the Fresnel equations? Right, and Snell's law. Right, so you have light beam comes in, gets reflected. The angle is exactly coming out to the same angle as it comes in. Well, if you go back and look at how the equations for the Fresnel equations were derived, you see that at some point somebody just said, let's assume for the moment that the mirror is infinitely large. So the question is now, what happens if the mirror is not infinitely large? Well, it turns out these equations are not correct anymore. So if you have, for example, polarization, linear polarization, it comes in, it goes like over and then comes out. If you send in circular polarized light, it goes onto a mirror, goes to the side, and comes out. That actually has to do with angular momentum conservation. And so these effects are small. They're on the order of, fractions of a wavelength. So let's say 50 nanometers or so. Now the thing is that we tried to look with polarimetry at exoplanets on big telescopes, and there was something that prevented us from doing that. Close to the star, we could never, ever get a decent signal. And now that we understand how these Fresnel equations are different, we actually plopped it into our simulations, and you know what? We almost exactly reproduced what we saw at the telescope. So doing polarization of exoplanets at these levels is incredibly difficult, and nobody really thought of this before, and so it will be a while until we have actually built telescopes that do not have these effects, or we can somehow compensate for them. So it's a real mess. The paper was just published a few months ago. Very proud of my grad student for doing this. This was a lot of hardcore theory, but it exactly matches what we see at the telescope. So we're pretty sure we got it right.
We are out of Lowell passes, but I did have one more Lowell sticker in my office. So we got one more question today, and then we will thank our speaker one more time. So anyone else today have a question? Oh, Breck, your hand beat Amanda's by just a moment. All right. What's your question, Amanda?
My question is, are you planning on kind of combining the two, I can't remember the word, making the ring dark around the sun and then also the polarization of the light? Are you planning on combining them to make like one like quote unquote perfect instrument, or is it they are two separate things and they can't be put together?
No, in the end, we want everything to be combined, right? You need to basically pull out all the tools you have. Every single trick you have up your sleeve, you have to shake out and combine it. And the reason why things have been difficult so far is that people optimize a single thing, like they optimize the adaptive optics. But they didn't realize that they completely screw up the polarization of the light that goes through. Or you have adaptive optics and then you add a coronagraph, but the two are individually optimized, not as a system. So that's why for the last 15 years or so, I've always said systems engineering. And we actually developed a course on systems design for astronomers, because everybody's so focused on their speciality that works fine. These days, there's also a lot of computational efforts, right? If we calculate what these holographic masks have to be, there's a ton of computational power that's behind it. And these days, we largely use the infrastructure from AI and machine learning to actually do that.
Got one more.
Yes.
I feel really special. I get to ask my question. Okay. So with the device that you made that you can point at a forest and it'll tell you something's living there.
Yep.
How far away from the Earth would you need to get before you get like a general sense of what you'd find from the Earth?
Very good question, because that's really a huge issue, right? We can go on the ISS or we can launch a CubeSat, but that looks at such a small part of the Earth's surface that we don't really get the impression of the Earth as an exoplanet. So you really want to be away. We have figured out the moon is actually pretty good. You know, at least from the moon, you see basically half of the Earth. And it's a pretty good place. People want to go there. You can place things. You could say, well, why not to geo, for a geostationary satellite or something like that? Well, that always sees the same part of Earth, right? You don't see it rotate. And so we think actually the moon is a pretty good place to be to look back at Earth. Of course, you could go to L1 or L2, but that's probably fairly cost prohibitive. We have been working with 2 commercial companies to try to put something on their landers, but you know, as many space startups go, they went bankrupt, and that's the end of it, right? But we actually, with a Dutch company, we have a pretty good instrument design that can go on a moon lander.
Let's thank Dr. Keller again. As a reminder for all of you that were either brave and asked questions or shy and did not, please come at 3 o'clock. We have a conference room up in AC1 reserved for you guys to talk to Dr. Keller, ask about things with exoplanets or Lowell or optics or any of those things, so that you can understand more about the process of what he works on, along with his students and collaborators. So thank you again, and have a great day, everyone.